All right, here we are, recording another episode. We're going to talk about string theory today, a very high concept thing.
Here we go.
Are you ready?
I'm ready.
Let's get into it.
To answer this question, humans come up with stories to describe the world. We test our stories and learn what to keep and what to throw away. But the more we learn, the more complicated and weird our stories become.
All right, so this is about string theory. So obviously it's going to take a while for him to get into it. So let me click right to it.
Nature of everything. Why did we come up with it? And is it correct or just an idea we should chuck out?
All right, so this is string theory.
I say keep it for now.
Yeah, I mean, somebody worked really hard just to figure all this out. That takes a lot of hours to figure this out.
To understand the true nature of reality, we looked at things up close and were amazed. Wondrous landscapes in the dust, zoos of bizarre creatures, complex protein robots, all of them made from structures of molecules made up of countless, even smaller things, atoms. We thought they were the final layer of reality until we smashed them together really hard and discovered things that can't be divided.
So first of all,
here we go.
You got to even get to the concept of an atom, which does take time, right? You got to build all this like beginning knowledge, right? So first you just talk about the atom and you're like, that can't be real. That's all science ever really seems to do. It's just like once you start an idea, it's like most of the time, oh, you're crazy. And then they find out that they're right later.
Right.
Way
Not
later
as crazy as they thought initially.
Yeah.
That's right.
I think that's actually part of it, right? To keep the knowledge kind of suppressed or maybe take it away from someone to just say, oh, you're crazy. And then like when they're dead, just take all their stuff.
Vested interests want to hold on. You know, they don't want to let go of an idea that they believe true, even if evidence proves otherwise.
Yeah.
So they get all like, insecure or worked up about it. And
Allegedly, the U.S. government took all of Nikola Tesla's stuff and patented almost everything.
Oh, yeah.
And it still hasn't come out. They still have all that, the anti-gravitic stuff and all.
Anymore. Elementary particles.
Here we go.
But now we had a problem. They're so small that we could no longer look at them. Think about it. What is seeing? To see something, we need light, an electromagnetic wave. This wave hits the surface of the thing and gets reflected back from it into your eye.
Okay.
The wave carries information from the object that your brain uses.
That's pretty interesting, right? I was thinking about this the other day. So Alan Watts I was listening to, and he mentioned it. And he says, your ears will naturally just take in what you're hearing. It'll figure it out for you. Your brain will. And all our eyes are doing is taking in light and pulling it in, and our brain is sort of reading the data.
It's true. It's cool, isn't it? Just like our ears do the same thing for sound, our eyes do for sight, our nerve endings for touch. It's really cool. So that's basically all it is. Our brain's just interpreting the data.
Which I'm I would think so. We don't have the full gamut of light. There's probably a lot of things that occur around us that we don't even see. Just how like frogs have different sight than we do, or flies and things like that.
To create an image. So you can't see something without somehow interacting with it. Seeing is touching, an active process, not a passive one. This is not a problem with most things. But particles are very, very, very small. So small that the electromagnetic waves we use to see are too big to touch them. Visible light just passes over them.
Wow.
We can try to solve this by creating electromagnetic.
So wait, he said we can't actually see them. Our
I guess the light itself is the wave just passes over Earth.
Electromagnetic waves we use to see are too big to touch. Are very, very, very.
That's one part I didn't know.
Very small. So small that the electromagnetic waves we use to see are too big to touch them.
Okay, so we can't, the atoms, we can't see them. They're just too small.
You think we'd get lucky and the wave would hit one even by accident? But it's interesting, I guess.
I think they're just so microscopic that like we...
maybe that's the issue,
Visible light just passes over them. We can try to solve this by creating electromagnetic waves with more and much smaller wavelengths. But in quantum physics, shorter wavelengths means more energy. So when we touch a particle with a wave that has a lot of energy, it gets a kick. By looking at a particle, we change it. In quantum physics, we cannot know where a particle is and where it's going with absolute precision. This fact is so important that it has a name. The Heisenberg uncertainty principle, the basis of all quantum physics.
Heisenberg uncertainty principle. Of course, that sounds like there's a German involved.
Oh, yeah. And for Breaking Bad fans.
So what does a particle look like then? What is its nature? We don't know. If we look really hard, we can see a blurry sphere of influence, but not the particles themselves. We just know they exist. But if that's the case, how can we do any science with them? We did what humans do and invented a new story, a mathematical fiction. The story
of mathematical fiction. Wow.
That is interesting.
I don't think I've ever put those two words together, but when you do, that's something. Mathematical fiction.
I wonder what Dr. Stephen Hawking would say about that term, unless he would have said so himself. I don't know. That's really neat.
I'll segue off this a little bit. Wouldn't it be cool if people were more into, I always say the West. I'm always talking about America. I live here. I don't know. That if it was a lot cooler to pursue this type of knowledge, like in school, like many schools and all, if you start doing this kind of stuff, it's nerdy and dorky. And it's like, start listening to like negative music. And it's just like, you start idolizing money and chasing women and all. And it's like, I don't know. Can't we get a little more focused? Like we can procreate and mate as well and gain money, but can we get back to the good stuff, the history, the knowledge schools,
Might not be the best guy to quote, but Rick Sanchez from Rick and Morty, forget about all of this stuff, focus on science. That's what he tells Morty. You want to be happy, focus on science.
Yep.
I don't know if that's entirely true, but it would be cool. I'm with you.
I think it's cool because you get around other people who are academics and people who are seeking knowledge, and those are great people to be around. I know a lot when I grew up, but we were into stuff. You might be like, whoa, man, check this out. Like when you put the music, the Pink Floyd music to like the Wizard of Oz or something.
Heck yeah. Pink Floyd, man.
There are things, but we weren't sitting around trying to figure out how to invent something that's never been made, or how to.
No, that's very true. I can certainly say that for myself and my friends too. We weren't sitting around inventing the string theory or any other theory for that matter.
I'd like to think in our own way when we're chomping on these meta bullets that perhaps we are expanding our consciousness in a way.
I think so. I agree.
Of the point particle. We decided that we would pretend that a particle is a point in space. Any electron is a point with a certain electric charge and a certain mass, all indistinguishable from each other. This way, physicists could define them and calculate all of their interactions. This can be made precise in quantum field theory, and this solved a lot of problems. All of the standard model of particle physics is built on it, and it predicts lots of things very well. Some quantum properties of the electron, for example, have been tested and are accurate up to 0.000000000002%.
That's ridiculous.
That seems pretty good.
Are not really points.
Yeah.
That's some absurd math right there, man.
I know, right? When you got to do those exponents, it's like times 10 to the negative whatever power.
Sure,
that's a lot of zeros.
I don't even know what that confirms. I couldn't even quite understand what that absolutely. Wow.
I guess that they can their story is showing that they can get this location of this electron, if I understood it correctly, the electron down to that level of accuracy that can never get to a.
You have
100%.
To pinpoint it and have those two kind of collide with each other, right?
Mm-hmm. Yeah, so I guess that's the idea. Is like it's they can only go so far, at least as of today.
So mass, charge, magnetic moment. Okay, so the magnetic moment
have been tested and are
accurate
up
pretty
to
close and right.
0.00.
Yeah.
I think they're talking about, I'm going to butcher it, but the hydrogen collider or whatever. Do you know what I'm talking about?
Oh, yeah, that Large Hadron Collider they had in CERN in Europe, I think.
Yeah.
Yeah, that's
what that machine.
What they showed earlier in the video, I think, right?
That's what the machine is doing. It's smashing them together, and it's creating little black holes and like little destructions of universes, or it's doing that that spark that is It's fascinating.
By treating them as if they were, we get a
I'm so stupefied that I'm stuttering throughout this video, and I normally don't
I know it's hard. I don't even fully understand the concepts myself.
It's kind of funny. Usually I'm always very composed and just know what I'm going to say. That's string theory for you.
A good picture of the universe. Not only did this idea advance science, it also led to a lot of real-world technology we use every day.
Nice. Here we go.
But there's a huge problem: gravity. In quantum mechanics, all physical forces are carried by certain particles. But according to Einstein's general relativity, gravity is not a force like the others in the universe. If the universe is a play, particles are the actors, but gravity is the stage.
Wait, okay, hold on. I want to hear that again.
Oh yeah, I've heard of the general concept.
Gravity is not a force like the others in the universe. If the universe is a play, particles are the actors, but gravity is the stage. To put it
Particles are the actor, but gravity is the stage. Okay.
simply, gravity is a theory of geometry, the geometry of space-time itself, of distances which we need to describe with absolute precision. But since there is no way to precisely measure things in the quantum world, our story of gravity doesn't work with our story of quantum.
There's no A to B. There's no direct.
At the quantum level, it's it doesn't work anymore. It's why they're kind of chasing scientists. I'm really simplifying it, the so-called unified theory. How do we match the theory of relativity and what we see in like our world at our level with what we know so far of the quantum level? There seems to be a big disconnect there. That's what I understand of it. I mean, any scientists out there want to correct me, please do.
These are extremely high concept ideas, and then they're backed by, people who have spent a whole career in the math.
Yeah.
And, I mean, Einstein's been dead a while, but like, I think he's probably one of the most talked about dead people. Like, he's not dead.
Probably right about that. Yeah.
He's very much alive.
Very much alive. Yeah. Well said.
He's not dead.
Physics. When physicists tried to add gravity to the story by inventing a new particle, their mathematics broke down. And this is a big problem. If we could marry gravity to quantum physics and the Standard Model, we would have the theory of everything. So very smart people came up with would have the gravity to quantum physics.
So you got to put gravity with the Standard Model of quantum physics. Okay, so you're really just trying to combine two things, many things, because that Standard Model was obviously many ideas and a lot of work.
Yeah, a lot of work went into that too, and it works at our level. Like I drop my computer, I can count it's going to hit the floor right at a certain speed on Earth. But it's like at the quantum level, it's like the rules almost contradict each other. I mean, in a simplified sort of way.
I think it's wild, man. That thing I hear about often that I don't know a lot about, but I kind of instinctually agree with it, is how there's like two things that can be connected to each other, but they can be very far apart in the universe.
Oh yeah,
but they have
quantum entanglement.
Correct.
Right,
and they both are sort of connected, and it's like maybe one and the other could switch, so you can go like very far distances, like I don't know what those things are that move like that, but it seems like there's a polarity that is absolutely abstract, but that's just because we don't understand it. But I think that probably is kind of real. I think that's kind of how the universe, like, you move throughout it,
Oh yeah, it's true. That's true. We are constantly in a state of, when you think about it, it feels like we're sitting still on a planet, but we're constantly in motion.
We're spinning
at all times. It's good.
There's one thing. Let's keep this about a 15-minute video, so we'll wrap this up here.
Sounds good.
There's one thing I heard from Back to the Future. Well, they talked about it. Somebody talked about Back to the Future. So how they go to they go back and forth in the movie.
That's right.
Different time, right? They have to make sure that they're going to the right month and the right day. Otherwise, the Earth wouldn't be where the car would appear.
Oh right, yeah. Because if they, I see what they're doing there. If they mess that up, they're suddenly
in outer space,
lost in space. Yeah.
If they're not exactly in the very perfect spot that the planet has to be in its rotational, you wouldn't even be in our gravity. You wouldn't even be in our habitat. You wouldn't be in the air. You'd be in the middle of nowhere, utter darkness.
Oh God, that sounds
Marty,
terrifying. Actually, Marty. Yeah, that sounds terrifying.
I mean,
no one would hear them. I mean, outside the car because in space, the old
perhaps Doc Brown could just move again and recalibrate. But I mean, it would be a bit shocking if you think you're going to see Biff, and then you don't see.
He would still be going 88. Oh, was it 88 miles an hour? Was that how he had to reach that certain speed?
Yeah. No, you're right. You're not going anywhere. You're just gonna. But
man,
that was a fun one. We couldn't do all that, but I feel like we definitely dipped our toe in string theory.
Oh, that we did.
And thank you. That was fun.
Thank you.
I was like, wait, I'm stuttering. I'm like, I'll keep the stutters in. I don't know. I was stupefied.
Totally worth it. Hey, me too. I'll be honest.
Well, that was cool. I did learn a little bit, but with that, we're out.
Oh, yeah.